29 iterations, the agents we've constructed have operated with a profound safety net. From simple data retrievers to the collective intelligence meshes orchestrating entire server grids, they have all lived entirely within the digital realm. That changes with Agent 30. The Embodied Intelligence Agent marks the terminal stage of our engineering progression. We are taking the artificial reasoning stack and giving it a physical body. In a purely software environment, failure is cheap. A hallucinated database query throws an error. A bad routing decision triggers a retry protocol. You have the luxury of transactional rollbacks, caught exceptions, and the undo command. But the physical world offers no rollbacks. When an agent actuates a mechanical limb or accelerates a chassis, it earns every decision against gravity, momentum, and friction. A bad output here does not crash a server. It causes irreversible kinetic damage. This reality forces a complete architectural redesign. We can no longer rely on software to simply catch its own mistakes. In 1966, researchers built Shaky, a wheeled robot navigating laboratories using pure reflex. It possessed no deep strategic thought, but survived through ultra-fast kinetic reactions. The limitation of pure reflex is that it is entirely blind to context. A reflex system will flawlessly avoid hitting a closed door, but it lacks the semantic understanding required to reach out, turn the handle, and pass through it. Modern large language models solve the semantic problem perfectly. They can process complex objectives, understand spatial context, and construct multi-step strategic plans for interacting with an environment. But LLMs introduce a fatal latency mismatch. A warehouse robot needs a 100-millisecond response to avoid humans. An LLM takes seconds to process prompts. By the time it formulates a perfectly reasoned stopping protocol, the chassis has already crushed its target. This is the central paradox of embodied intelligence. We have a slow, deliberative brain and a fast, reactive body. We have to merge them without the latency gap causing a catastrophic physical failure. The solution is a counterintuitive architectural rule. The slow language model and the fast actuators must never be directly merged. We engineer this through the asymmetric control loop. This pattern explicitly decouples asynchronous deliberation from synchronous control. The LLM provides the why and what at a slow pace, while a deterministic non-AI controller manages the how in real time. A more capable language model does not equate to a safer machine. No amount of advanced reasoning guarantees survival when facing physics. In an embodied context, safety is not a learned behavior. It is defined as a rigid mathematical boundary known as the admissible action set. We do not trust intelligence with physical safety. Instead, we structurally constrain the intelligence behind non-negotiable physical boundaries. This flow diagram illustrates the complete four-layer control architecture enforcing these boundaries. At the highest level, an operator issues plain language intent. The task planning layer uses an LLM to interpret this goal, operating at a slow 0.1 to 1 Hz to map out the strategic sequence. Before any of those plan steps move forward, they hit the A safe of S safety gate. This validates the LLM's plan against current physics. If the agent hallucinates an impossible maneuver or proposes an unsafe trajectory, the gate instantly rejects it and forces the LLM to replan. Approved commands then enter the multi-rate control tier. Speed escalates drastically here. Motion planning computes collision-free paths at 10 Hz, passing trajectory parameters down to servo loops that regulate raw motor currents thousands of times a second. At the absolute bottom sits the ultimate failsafe, the hardware emergency stop. This mechanism completely bypasses all software intelligence. You cannot talk it out of stopping. Complex reasoning flows downward slowly, while raw physical sensing flows upward rapidly. To make strategic decisions, the top-level LLM needs to understand its environment. But raw sensor data, unfiltered LiDAR point clouds and raw camera frames, is far too volatile and noisy to feed directly into a slow planner. Instead, the agent maintains a belief state. This is not a direct photograph of reality, but a probabilistically fused world model. Algorithms like Kalman and particle filters run at 10 to 100 Hz, constantly digesting raw telemetry. They smooth out environmental anomalies, handle contradictory depth estimates, and infer true object positions. This filtered model insulates the slow planner from the stochastic noise of the physical world. The reasoning intelligence never directly touches raw reality. It calculates its strategies exclusively against this sanitized, mathematically stabilized digital twin. This Python script shows exactly how this asymmetric boundary is enforced in the execution loop. In step 1, the LLM agent is invoked to reason about the task. It produces structured output, and step 2 extracts those proposed physical actions. Step 3 is the critical intercept. Before the control interface ever sees the command, it is passed to the safety monitor. This evaluates the proposed action against the admissible action set. If the action violates a physical constraint, the agent is halted. The rejection reason and specific broken constraint are packaged into a system prompt and fed directly back to the LLM, forcing it to generate a new, compliant plan. The codebase structurally boxes the unpredictable, slow planner within non-negotiable, fast physical constraints. The AI proposes, but the deterministic layer decides what happens. We can observe this architecture under severe stress by deploying an autonomous drone to conduct a 6-kilometer survey corridor over the Ottawa Riverfront in sub-zero winter conditions. To fly, the agent must satisfy a unified constraint envelope. This constantly tracks ambient temperature, wind speeds at altitude, the battery's state of charge, and the presence of freezing precipitation. It must also simultaneously satisfy regulatory constraints, verifying airspace rules through Transport Canada and cross-referencing overflight authorizations from Parks Canada. The system operates on a rule of conservative constraint fusion. If a single metric from any domain fails, say a sudden drop in ambient temperature below the operational threshold, it instantly vetoes the entire mission envelope. True embodied intelligence must simultaneously satisfy hard limits from local weather, hardware physics, and federal law before a single rotor is allowed to turn. In 2012, Amazon spent $775 million acquiring Kiva systems. Their robots were slow, locked to flat surfaces, and possessed very limited edge intelligence. But a fleet of 800 simple robots completing fetch tasks with 99.8% reliability moves far more product than a dozen bleeding-edge robotic arms that fail unpredictably. Fleet-level reliability and graceful degradation matter vastly more in the physical world than isolated intelligence. Over this series, we have built architectures that retrieve data, generate code, process audio, and orchestrate complex networks. Agent 30 acts as the terminal node. The embodied agent inherits the vision systems, the memory persistence, and the tool calling logic of every agent that came before it, finally grounding those digital capabilities into the physical world. The ultimate takeaway of AI engineering is this: an intelligent system in the physical world is a liability unless it is housed within a rigorous structural architecture that prioritizes safety over smarts. To explore the Python implementations for the asymmetric control loop, the belief state, and the complete rosters of all 30 architectures, read 30 Agents Every AI Engineer Must Build by Imran Ahmed and access the open source code repositories at Pact Publishing.